Hello guys, this is Saeed Mohammad Wakas. I'm back with another video. The topic which I'm going to discuss today is related to the hot water recirculation system, and this topic is very important, so please make sure to watch the video all the way till end, and don't forget to subscribe my channel. So let's start hot water recirculation system design. So as you can see that there I have prepared an Excel sheet, and I have taken an example of 24-story building, and we're gonna design the hot water recirculation system for that 24-story building. So here I have a table also which I'm gonna use. So first thing you have to do here is you have to write your risers, all the risers in here which you have shown here in the figure. So as you can see that I have given the name for each riser, like riser 1, 2, 4, 3 and up till 11, and hot water piping is already shown here in the drawing, as you can see that. So if I will zoom and you guys can see, this is our water heater installed in the basement, and this is the hot water supply piping. This is the hot water supply piping from here, and if you see that this is going all the way up till 24 story, and then there's a recirculation piping, hot water recirculation piping, and this recirculation is going back into the heater. So we are going to design this recirculation lines. So we are going to design the risers, and we're going to design the main for recirculation system. And hot water piping is sizes are already mentioned in here. So if you remember that I have made a video on domestic hot water pipe sizing. So if you don't know how to do this hot water pipe sizing, you can go back to my channel and you can watch the video about domestic hot water pipe sizing. So I have to write all the risers in here, and main also. This is the risers, and this is the main from risers to one riser to another riser. That means this is the horizontal pipe. You can see that this is the horizontal pipe for recirculation, this one. So first you have to do is you have to write the hot water pipe sizes here, and the second thing you have here is hot water piping BTUs, loss per hour per unit length. So this is you have to write in here, then you have to write the length, and then hot water piping BTUs loss per hour based on this length, and then you have to calculate this hot water recirculation piping BTUs per hour, and in the end you have to calculate this GPM to overcome the heat losses. So first of all I'm gonna take main from heater to the riser 1. So as you can see that this is the heater which we have in here, and this is the hot water supply piping. You can see in here this, and size of this pipe is 4 inches, hot water supply pipe, and sizes for recirculation pipes are unknown, so we are going to calculate. So this hot water supply pipe size, you can see that it's 4 inches up till this point, and this point is riser 1, and then again you go over here and you will see the size is same, 4 inches, 4 inches, 4 inches, you can see here. So from this point 3, riser 3, size is changed to 3 inches, then you have 3 inches up till here, this point 14, riser 14. So after that your size is changed again to 2.5 inches. You can see here 2.5 inches, again 2.5 inches, and then here you have 2 inches. So if you see from main, from heater to riser 1, so heater to riser 1 we have write 4 inches in here. So same way which I have told you, you have to write the sizes from riser 1 to riser 2. That means from riser 1 to riser 2 there's a main pipe in here, and size is 4 inches, you have to write 4 inches. And from, let's say we take another, like riser 12 to 14, how we get 3 inches. So this is 12 and this is 14. In between them we have horizontal pipe, the main pipe, and you see that the size is 3 inches. Hot water pipe size is 3 inches. So we have write the inches. So in the same way you have to write the pipe sizes here one by one for the hot water. And hot water piping BTUs, how you will get this one? So you have to use a table for this thing. So you go back here and you check the piping heat loss per linear feet for 140 degree Fahrenheit water supply temperature and 70 degree Fahrenheit room temperature. Here if you see that we have bare pipes and insulated pipes. So if you have a bare pipes without insulation, you have to use these values. If you have insulated pipe, you have to use this column values. Since our pipe is insulated, half-inch fiberglass insulation, so this one. So first I have 4-inch pipe size, so I have to write the heat loss value for 4-inch pipe size with insulation. You see that it's 46, so I have to write 46 value in here. So same way you have to write one by one. So let's say 2 inches. 2 inches is how much? 28. So we have BTUs per hour. So we have to write 28 in here. So once this is done, you have to go for the next column, that is length. Length is very simple. You just have to go to your AutoCAD plan and you have to measure the length from one point to another point. So as per the AutoCAD plan, you have to check the lengths and you have to write lengths here. So I already write the lengths here. So if you can see that lengths are already mentioned here, like 20, 10, 10, 10, 20, 20, 30, 20, 20. So according to that I have write all the lengths in here. So you just have to check it from the AutoCAD and write in here one by one. Now the next column is hot water piping total BTUs loss per hour. How you will get this value? Now we know that the length of the pipes and we know that BTUs per hour per unit length. So you just need to multiply these two figures, then you will get the hot water piping total BTUs loss per hour. So one by one you have to just multiply these two, like hot water piping loss per hour per unit length into length, you will get the hot water BTUs per hour. So one by one you have to calculate for all of the piping. So next thing over here is the hot water recirculation. This is the main thing which we are focusing on because this is the hot water recirculation system design. So if you see in here, hot water recirculation piping BTUs loss per hour, this you have to calculate in here. And how you will get this one? Since we don't know the recirculation pipe size, this is what our case that we want to calculate the sizes for the recirculation system, hot water recirculation system. So we don't know the sizes for hot water recirculation system. So there is an assumption as per IPC, International Plumbing Code, or ASPE, American Society of Plumbing Engineers. But we have to do, there's a standard that we can, if we don't know the sizes, we can take 2 by 3 of this value. Which heat loss we calculated here, we can take 2 by 3 of this value. 2 by 3 means 0.67. So you just need to multiply this value with 0.67 and you will get the hot water recirculation piping heat losses. So one by one you have to multiply with 0.67. So this is a standard value as I told you as per IPC. So you have to calculate one by one for the hot water recirculation piping heat losses. So next thing you have to calculate here is the GPM, that is gallons per minute, to overcome the heat losses based on 20 degree Fahrenheit temperature difference. As we mentioned earlier that supply temperature from the heater is 140 degree Fahrenheit. So based on our assumption of 20 degree Fahrenheit temperature difference, that means hot water supply temperature is 140 and recirculation is 120. So based on 20 degree Fahrenheit we have to calculate the GPM to overcome the heat losses. So how you will get this one? You just need to add these values, that is for the hot water piping plus hot water recirculation piping divided by 10,000. You will get the GPM. So how did I get this 10,000 value? So I will tell you also how I get this one 10,000. So as we know that 1 gallon of water weigh 8.3 lbs, you can check over the internet that 1 gallon of water weight is 8.3 lbs, so pounds, and 1 BTU is equal to heat necessary to raise 1 degree Fahrenheit, and recirculation for 1 GPM. Since it is based on 20 degree Fahrenheit, so we just need to multiply this 8.3 based on 20 degree Fahrenheit, so you will get 166 BTUs per minute. So if you want to convert into hour instead of minute, you just need to multiply with 60 and you will get 9,960. That is almost equal to 10,000. So this is why I have divided this value with 10,000. So one by one you have to get these values over here in this column. For this one you just need to add hot water piping total BTUs plus recirculation piping BTUs divided by 10,000. You will get the GPM in here for that particular section of the pipe. So that means main from riser 8 to 10. This is our riser 8 and this is 10, and this is the main in here, horizontal pipe. So the GPM over here is 0.13 GPM, which we have right in here. So this is done. After that we'll go for the risers. So if you see that riser 157, I write it combined because the length was same. That's why I write 157 together, and 2414 I write together because of the length. So I have write together all of these just because of the length. So if you go for riser 1, 5 and 7, so 1, 5 and 7, so you have to check their lengths from the AutoCAD plans and you have to write the lengths accordingly. So riser 1, if you see that which pipe do we have in riser 1, hot water piping. I'm talking about the hot water piping, what we have here in riser 1 for the hot water piping. So if you see that in the riser 1 we have 2.5 inches, 2.5 inches, 2 inches, 1.5 inches and 1/4. So we have to write all this pipe there. You can see that 2.5, 2, 1.5 and 1/4. So all of pipe you have to write in here accordingly. And again you have to get this hot water piping BTUs per hour per unit length from the table. So 2.5 inch pipe, how much it is? 32. So 1/4, how much it is? 21. That is 21. So this is how you have to write one by one for each pipe size. So length, again I am telling you, you have to check from the AutoCAD plan and you have to write it. So I already write the length in here. So 160 feet, 27 feet, 18 feet and 6 feet. And for what you have to do, again you have to multiply in order to get your hot water piping total BTU loss per hour. You just need to multiply the length with per unit length BTUs loss. So you will get the total piping loss in BTUs per hour. So same way you have to do for this one and this one. So once you are done with this, you have to just get the total of this value, total heat loss for the hot water piping. And this one is again same assumption, we have to take 2/3 of this value because we don't know the pipe size for recirculation system. So we are going to take 2/3 value of this one. So if you multiply this with 0.67, that is 2/3 of this value. It is 4,323 BTUs per hour for recirculation piping heat losses. And this thing again you have to calculate sum these two values and divide by 10,000. You will get the GPM, 1.08 GPM. So as you know that this is for one riser which we have calculated, and here if you see that we have three risers, that is 1, 5 and 7. So if we have three risers, that means you need to multiply this value with 3 and this value with 3. So I already multiplied this with 3 and this with 3. So we got the total BTUs for hot water piping and hot water recirculation piping heat losses for three risers. This is for individual riser and this is for three risers. So same way you have to other risers 2, 4 and 14. So I'm gonna take one more here just to save the time. I'm not gonna do for all of these. So I'm gonna take one more example here for riser 6. So if you see riser 6, so we will check now, check the pipe sizes in riser 6. So this is riser 6, and if we check the pipe sizes, this is 1.5. This is the hot water pipe sizing again. This is 1.5, this is 1/4, 1/4 and 1 inch. So we have 1.5, 1/4 and 1 inch, three pipe sizes here. So 1.5, 1/4 and 1 inches. That's how we write the pipe sizes in the riser. and we will write the heat loss values for each. Same way, you have to check these values from this table and you have to write in here. And these lengths you have to get from AutoCAD plans and you have to write in here. And hot water piping BTUs per hour, you have to get, just multiply this per unit BTUs per hour loss for hot water with this length. You will get the total hot water heat loss per hour for the hot water piping. So one by one you have to calculate for all pipe sizes and then you have to sum it up in here. And then what you have to do in here is you just have to calculate the second one, that is 2 by 3 of the total value, 2 by 3 of the total value. So you just need to multiply this with 2 by 3, that is we are taking 2/3 of this value, that is 0.67, and you will get the heat loss for the recirculation piping, hot water recirculation piping. So in the same way you have to get the GPM. You just need to sum up hot water piping BTUs per hour loss and recirculation hot water piping and divide by 10,000. You will get the GPM, that is 0.80. So this is how you have to calculate the BTUs and GPM for the remaining risers. So here we have 4 risers, you can see that. So you need to multiply with the 4 to get the total BTUs, and you need to multiply with 4 to get the total heat loss for recirculation and hot water piping. So after that what you have to do is you have to sum up your heat losses for hot water piping and recirculation hot water piping. So if you sum up the hot water piping heat losses, it's around 95,534 BTUs per hour, and if you check for recirculation losses, this one is around 64,000 BTUs per hour. Hot water recirculation piping loss 64,000. So total recirculation rate will be how much? It will be the sum of both hot water piping plus hot water recirculation piping. That is 1,59,542. That means almost 1,60,000 or 160,000 BTUs per hour. So how you will get the required flow rate? Required flow rate, how you will get? You just need to, same way, you just need to divide the sum of these two, that is hot water piping heat loss plus hot water recirculation piping heat loss, divide by 10,000 to get the required flow rate. So required flow rate for our system is, required recirculation flow rate is 15.95 GPM. So 15.95 GPM is required. And if you check in here, the next thing is uniform friction head loss. It is recommended to have a uniform friction head loss of 2 to 4 feet per 100 feet. So here we have taken 3 feet per 100 feet uniform friction head loss, and develop length of the run which we have to calculate, that means from heater to the most remote riser. So this is our heater and most remote riser. If you see that this is our most remote riser, that is 11 at story or floor number 11, floor number 24. We have the most remote riser, that is 11. So from here recirculation piping, if you check that hot water recirculation piping to the heater, this is our developed length total to the most remote riser, that is 11 number riser. So if you check from the AutoCAD plan, you can get these lengths, and according to that you have to write your lengths. So this is for the riser, due to the riser 207, this is from the riser recirculation 207, and this is for the horizontal piping to the main, from main to the heater. So 207 is due to the riser and 275 is the main piping length. So total is 482 feet is the developed length. So how we'll get the equivalent length of run? Since we don't know the sizes for recirculation, so we're gonna apply the general thumb rule for fittings to get the total equivalent length of run. So we know that the total piping length for the straight piece of pipe, but we don't know for the fittings and the valve. So what we're gonna do is we're gonna take 10% of this value to get the equivalent length of run. So you can see that this value plus 10% of this value, so we'll get 530 feet is the total equivalent length of run. So now we know that equivalent length of run, and we know the friction head loss, that is 3 feet per 100 feet. It is recommended value 3 feet per 100 feet. That's why we have used this one. If you increase this value to 5, 8 or 10, you will have more losses. That's why we have selected 3 to have a uniform losses. So if you want to calculate the head required now for recirculation system, so how you will get that? You just need to multiply this uniform head loss with the equivalent length which we have calculated in here divided by 100. You will get the head. So head for recirculation system required is 15.91 feet. That means 16 feet head is required for the recirculation system. And GPM we already calculated, that is 16 GPM. So now the last thing which we have to do here is we have to size the hot water recirculation system. This is very important. So how we did this thing? So basically I have used this formula. For the brass or the copper piping you have to use this equation, and for galvanized or steel pipe you have to use this equation. Since we have a brass or piping, so we have used this formula. So we have the H value, head, we know that 16, and length, it's per unit length we have calculated here. So if you, and Q we also know that is 16 GPM in here. So if you know all the values in here, so the thing which remaining is D, that is diameter for piping. So you can calculate easily after putting all the values. So based on this thing, there is a formula developed in here. If you change the GPM one by one, you will develop this this thing, that is half inch is equal to 1.8 GPM. So from this equation I got this values: half inch equal to 1.8 GPM, 2 inch equal to 34.6 GPM, and 4 inch equal to 181 GPM. So now we are going to use one by one to calculate the recirculation pipe sizes. So one more thing, if you have to check in here, for all the risers, if you see that GPM is 1.08 for 157, and 2, 4 and 14 GPM is 1.02, and 1.14, 1.80, 1.04, 0.92. So you can see that minimum GPM here is 1.8 GPM, and all the GPM which we have calculated in here for the risers are less than 1.8 GPM. So the minimum size, if you see that here is half inches available, that means our riser will be half inches, all the risers, because their GPM is less than 1.8. So we can use half inch in here, but we will not gonna use half inch. The minimum size recommended is 3 by 4 inches. So instead of half inches, we're gonna use risers 3 by 4 inches. The reason why I'm gonna use 3 by 4 inches instead of half inches, because pipe size will be very small, and with the time maybe deposits will be developed inside the pipe and it will gonna block the pipe. So it is better to use 3 by 4 inches pipe size instead of half inches, even if it is 1.8 GPM. So I'm gonna use minimum pipe size is 3 by 4 inches for all the risers. If you see that all GPMs is less than 3.5, so all the riser size for the recirculation hot water, it will be for risers, it will be 3 by 4 inches. So riser size is done, 3 by 4 inches. Now what we're gonna do, we're gonna calculate the size for the main recirculation piping in here, like between 9 to 11 riser, between 6 to 9 riser, between 5 to 7, between 1 to 2. We have to calculate the main horizontal piping. So we'll do one by one. So first is riser 11. So it start from the most remote one. If you see that this is riser 11 in here, and we're gonna get the size for this main pipe, main recirculation pipe in here, which is connected to water heater in here. So we'll go one by one and calculate one by one size to the water heater recirculation pipe sizes. So here you have section 11, this is riser 11, and we are going to get the size for this horizontal pipe in here, this one. So this is we have 11. If you see here, this is riser 11 plus main 9 to 11. first we calculate the GPM, and based on GPM we'll get the sizes. So between 9 to 11, if you see that how much is the GPM we got from riser 9 to 11, this one, if you see the GPM is 0.12 between 9 to 11, between 9 and 11 riser, and 11 riser is how much GPM, riser 11, this one, remember that 0.12, and riser 11 is 0.92, so 0.92 and 0.12, so 0.92 plus 0.12 is 1.09 GPM total. So if you see that 1.09 GPM based on the assumption and based on the values applied to this formula, we got this thing. So 1.09 is less than 3.5 GPM, so we can use 3x4 inch pipe size in here. So we're going to use 3x4 inch pipe size for this one. So that means we can use 3x4 inch pipe size up till 3.5 GPM. If we have 3.6 GPM, then we have to increase the pipe size to 1 inches. So I'm gonna take another example in here. So let's take second one also, 1.04. So 0.92 plus 0.12, it is 1.04, sorry. So let's take the second main pipe size. So now we will calculate the size for the second one here, second one. So if you see the second one is riser is 9, we have to add this value also, which we calculated earlier. This value, first value which we have calculated here, plus riser 9 GPM value, plus between sections riser 6 and 9. So if you check previous value which we'll add, that is 1.04, which we have right in here, plus riser 9 plus main 6 to 9. So if you see that riser 9 GPM is how much, you see here, that is 0.92. So we have to write riser 9 0.92, and the last one here is main 6 to 9. If you check the main from 6 to 9, this one GPM is how much between 6 to 9. So main from riser 6 to 9 GPM is 0.11. So you have to write 0.11 here. So you know all the GPMs now, just add it, total it will be 2.07. Again 2.07 is less than 3.5 GPM, so we can use 3x4 inch pipe size. So we have used 3x4 inch here. So I'm gonna use some other example here now. So let's say I'm going to calculate for this one. So you have to consider the previous one also. Previous one is 11.34 plus riser 3 and main 4 to 3. That is main is this one, riser 3 and main 4 to 3. So if you see that riser 3 is in here and 4 is here, so we have to check GPM for this riser 3 and all the GPM, previous GPMs here, plus riser 3 GPM to get the size for this pipe segment. So what you have to do is GPM for riser 3 and GPM for between riser 3 and 4 and the previous all GPMs. So riser 3 is how much, 1.14, and between 4 to 3 is 1.08. So you can see that riser 3 value is 1.14 and 0.08 is for main between 4 and 3, and this is the previous GPM which we have to add in here to get the size for the next pipe segment. So if you see that total which we calculated here is 12.56 GPM. So 12.56 GPM, if you see here, it's 12.4 GPM. Up till 12.4 GPM you can use 1/4 inch, but since this 12.56 is greater, so we have to increase the size to 1.5 inches. So that's why we have used 1.5 inch for this pipe segment. So you can use 1.5 inches up till 18.3 GPM. You can use this size. After that you have to increase the size again. So one more last item I will tell you here. Same way you have to do for this one also. So last item is riser 1 plus main to heater. So if you see here, so last item we have riser 1 and all the previous GPM which we have calculated to get the size for this pipe segment. To get the size of this pipe segment, you have to add all the GPM which you have calculated in here plus riser 1 GPM, and this main pipe GPM, recirculation main pipe GPM. So from section 1 to the heater. So if you see that from heater to the riser 1, how much is the GPM we calculated? 0.15. And the riser 1 GPM, how much we got in here? That is 1.08. So 0.15 and 1.08. So if you see here, 1.08 for riser 1 and 0.15 is for main to the heater 1, and 14.6 is the previous GPM which we have calculated. So adding all these values, you will get 15.99 GPM total. So 15.99 GPM is less than 18.3 and greater than 12.4. So that means we can use 1.5 inch pipe size in here for that pipe segment. So this is how you can do the hot water recirculation pipe sizing, or you can design your hot water recirculation system. In this video I will tell you guys about water supply pipe sizing, cold water and hot water, both of them pipe sizing. So here you can see that I have a drawing for 2-story factory building equipped with 2 toilet rooms. As you can see over here, first one toilet room and the second toilet room, and the highest fixture you can see from this is the street main over here. So highest fixture is located over here. This is the 8 feet and this is 13 feet. So total height is from street main to highest fixture is 21 feet. So highest fixture is located 21 feet above street main. And over here in the street main we have a 2-inch corporation caulk at street main, 2-inch corporation caulk, and pressure loss through that caulk we can get it from supplier. And minimum pressure available at street, this is the street main, and the minimum pressure available at street main is 55 psi. So this value you can get from local water authorities on your location. And let's move to this tab. So this is the table we are going to use to calculate hot and cold water pipe sizing. As you can see over here, the things which I already mentioned before, like minimum pressure available at street main is 55 psi. This value you can get from the local water authorities on your area. So highest pressure at the fixture is 15 psi. As you can see that this is the highest fixture we have over here, and as explained that the highest fixture group is consist of flush valves. So basically you need to understand 2 things first. If you have a highest group of fixture contain flush valves, then the pressure for that group should not be less than 15 psi. This is as per International Plumbing Code IPC. And if your highest group of fixture contain flush tanks, then the pressure for that group should not be less than 8 psi. Since we have flush valve over here, so that's why we took 15 psi as per International Plumbing Code IPC. So that's why we have 15 psi is the pressure loss for this highest pressure required at the fixture. And we have a 2-inch water meter over here, 2-inch water meter. As you can see in the drawing, there we have a water meter over here, it's 2-inch, and the pressure loss to that meter you can get that from supplier. As you can see that the pressure loss we got from supplier manufacturer is 1.61, and the static head loss is 21 feet. Static head loss is due to the change in elevation. As you can see that from the street main to the highest fixture we have total height is 8 feet and 21 feet. So elevation difference is 21 feet from street main to the highest fixture. So
we got the static head loss is 21 feet. Since we know that 1 is equal to 0.43 psi per feet, so in order to convert this into psi, you need to multiply this with 0.43 psi per feet. So after multiplying this 21 into 0.43, you will get 9.03 psi static head loss. And then we have a special fixture loss like backflow preventer. Since you can see that in the drawing, we have a one backflow preventer over here, and this is 3-inch backflow preventer. We need to get this value, pressure loss value or friction loss value, from the supplier for the backflow preventer. So we get this value from the supplier, that is 9 psi. And if you have any other special fixture loss, like if you have filter or water softeners or anything, you need to mention over here these losses. So as you can see that we have mentioned each and every pressure loss with the different line A, B, C, D, E, F, G, H, I. So we need to add all these losses from point B to point H. So line B to line H, total losses 15, 11, 1.61, 9.039. So total friction loss is 45.64 psi. As you know that we get this minimum pressure at street main from local water authorities is 55 psi. So now we need to subtract this total pressure available at street main minus pressure losses through water meter, taps in the main, static head loss. We need to subtract all these losses. So this is the pressure available to overcome pipe friction, that is line A minus J. A is 55 and J is 45.64. So after subtracting, you will get 9.36 psi. So 9.36 psi is the pressure available to overcome the pipe friction. So now as you can see that we need to divide our into different sections. We have divided the drawing into a different section where major changes in elevation or branches lead to the fixture group. So A to B, this is one section, B to C one section, C to D one section, and D to E one, and then C to F another section. As you can see that how many fixture units we have over here: 288 fixture unit here, then we have 264 fixture unit here, B to C, and then 132 fixture unit here, 132 here, 132 here, and B to C we have 24 fixture unit, and then C to F we have 12 fixture units. And the lengths are given: A to B 54, B to C 8 feet, C to D 13 feet, and D to E 150 feet. So everything is mentioned in the drawing. So let's move back to our table. As you can see that we have a fixture unit for A to B is 288, then B to C we have 264, C to D 132, and C to F 132, and D to E 132. So now we have to get the gallons per minute through each section, because while doing water supply pipe sizing, we have to do it using a fixture unit, water supply fixture unit method. So load values of fixtures must be determined as water supply fixture unit. Then we need to convert them into gallons per minute to determine the peak demand. So we need to convert these fixture units into gallons per minute. So 288 fixture unit, then 264. So let's move to tables and charts over here, and we are going to use this table, this one 103.3. as you can see that this is the load, this is the demand, and this is for flush tanks, and this is the load demand for flush valve. Since we are using the flush valves, so we need to use this columns. So we have 288 fixture water supply fixture units. Since we have 275 here and 300 here, so we are going for the higher value for the safety. So 300 fixture unit, the demand will be 108 GPM. So move back there, 288 108 GPM. Then 264, how many GPM? 264 fixture unit, this is 250, and this is 275. So we don't have 264, we will go for the higher value, that is 275. 275 load, we will get 104.5 GPM load. So 104.5 GPM. So same way you have to check for 132 for each, you will get 77 GPM for each. So now we need to check the length of each section, A to B, B to C, C to D, D to E, and C to F. A to B is 54. As you can see, A to B is 54, B to C is 8, C to D is 13, and D to E is 150, and C to F is 150. So you can see that all the lengths we have mentioned here, 54, 8, 13, 150 and 150. So now the third thing is, in this column, column number 5, we have to check the trial pipe size. So the trial pipe size, how to get the trial pipe size? Trial pipe size, there is a formula which we have to use to get the trial pipe size. This is the formula, that is pressure available to overcome pipe friction divided by equivalent length of run to the most remote outlet multiplied by 100. So if we move back to our drawing, you can see that the most remote outlet is here. So total length from street main to the most remote outlet is how much? 54 feet, 8 feet, 13 feet and 150 feet. If you add all of them, how much length you will get? That is 54 plus 8 plus 13 plus 150. So total you will get 225 equivalent length of the straight piping. So we did not add any length for the fittings and the valves. So as a rule of thumb, we can add now 50% of the straight length of the pipe, just for now, as a trial pipe, for the trial pipe size. So 50% will be 112.5 plus 225 equal to 338. So total equivalent length of run is 338 feet. So now we know that the pressure available to overcome pipe friction, that is 9.36, we already calculated. We know that equivalent length of run to the most remote outlet, that is 338 feet, we just calculated now, multiply by 100. So pressure available to overcome pipe friction, as you know, that we calculated here, that is 9.36, this value. So 9.36 divided by 338, total equivalent length, multiply by 100. So how much friction loss we get? That is 2.77 psi per 100 feet. This is the average friction loss, that is 2.77 psi per 100 feet. So based on this 2.77 psi per feet as the average friction loss, and demand and the GPM, we already know that this is 108. So 108 GPM is the demand, and we know that average friction loss is 2.77 psi per 100 feet. So now we are going to use one chart. And one more thing, all the piping which we used over here is copper L type piping. So when we go over here, this is the chart for copper K type. Since we use this copper L type in our project, so we need to use this chart, that is 103.3 figure. So as you can see that on x-axis we have pressure drop in psi per 100 feet, and on the y-axis we have demand in the GPM, gallons per minute. So we know that we know that the demand is 108, and we know that the pressure drop is 2.77 psi per 100 feet. We already calculated here. So 2.77 psi over here and 108 GPM here. So it will be around 2.5 inch pipe size, as you can see over here, 108 GPM and 2.77 psi, that is 2.5 inch pipe size. So that's why we got 2.5 inch pipe size here, A to B section. Then B to C section, again we have how much GPM we have here, 104.5, and pressure loss will be same 2.77 psi per 100 feet, and GPM is 104. So GPM is 104 over here, and pressure loss will be same, so it's almost same, that is 2.5 inch pipe size. So we have used 2.5 inch pipe size. Now the third one is C to D, C to F, and D to E. We have same GPM, that is 77 GPM, and we know that average friction loss is 2.77 psi per 100 feet. So move back to our chart. 77 GPM is 50, 60, 70, 80. So just over here 77 GPM and 2.77 psi per 100 feet. It will touch somewhere here. So it is in between 2 and 2.5 inches. So for the safe side, we are going to select the 2.5 inch instead of 2 inches. So 2.5 inches pipe size for these sections. So now move to the next column, equivalent length of fittings and the valves. A to B, what fittings we have from A to B. So this is the table we have used for the fittings for the cold water pipe section, the hot water pipe sections. So A to B, what fittings do we have? If you move to the drawing, A to B, what fittings do we have? We have 1, 2, 3, 3 gate valves and 1 side branch T. 3 2.5 inch, we already know the size, so that's why 2.5 inches gate valves, and 1 2.5 inch side branch T. So this is the side branch T over here, and 3 2.5 inch gate valves. So now we have to get that equivalent length in a feet, pressure loss or equivalent length in a feet for these gate valves, 2.5 inch gate valves. So move back to our tables and charts. This time I'm gonna use 103.3 table. This one, as you can see that this is for the threaded fitting. Since we are using the copper tubing, so we are going to use this table over here. So we know that we have gate valve. You can see that we have a valve, gate valve over here, and 2.5 inch gate valve, and equivalent length is 1 feet. You can see 1 feet, and we have side branch T, 2.5 inch side branch T, and its equivalent length is 12 feet. So since we have 3 gate valves, 1 for each, so 3 gate valves, we have 3 feet. 1 2.5 inch side branch T, that is 12 feet, we already calculated. So now from section B to C, as from B to C we have only a straight run T, only one. So one straight run T, 2.5 inches. Move back to our chart, and this is our straight run T, and 2.5 inches. Straight run T is 0.5, equivalent length is 0.5. you can see over here 0.5, so 0.5 over here. Then C to F, then from C to F we have a side branch T. C to F we have a side branch T over here, and only one 2.5 inch side branch T. Size we already calculated before, trial pipe size, 2.5 inch side branch T. We already calculated 2.5 inch side branch T, that is 12. We can no need to go and check again. So C to D, now from C to D, what we have here, one elbow over here, size is same, 2.5 inches. So 1 2.5 inch 90-degree elbow, so we need to get its value from the table. You can see that elbow standard 90-degree, 2.5 inch, and its value is 7 feet. Equivalent length is 7 feet over here, you can see. So 7 feet. Then again from D to E, D to E, again we have a side branch T. As you can see over here, the most remote outlet we have side branch T, same 2.5 inch size. 2.5 inch side branch you already calculated, that is 12, so we can use 12 over here. So in the same way, the way I have calculated the friction loss for the fittings and the walls for the cold water, you can do for the hot water pipe sizing, and you can write it over here. So I don't want to make video much longer, that's why I will skip this part. If you have any query, you can ask me in the comment section below. So let's move back over here. So equivalent length of the fittings and the walls now we have to write over here. So A to B section, how much is the equivalent length of the fittings and the valves? As you can see that 3 and 12, so total is 15. Then B to C 0.5, C to F 12, C to D 7, and D to E 12. So 15, 0.5, 7, 12 and 12. We have write all the equivalent lengths in a feet. Now move to the next column, 7, total equivalent length. So now we know that the straight pipe length, and we know the equivalent length of the pipes and the fittings, valves and the fittings. So we need to add both of them. Straight pipe length section A to B is 54, and equivalent length of fittings from section A to B is 15. And we need to express this per 100 feet. So 54 plus 15, that is 69, divided by 100, it will be 0.69. So same way from section C to D is, that is 13 is the straight pipe length, 7 is the equivalent length of the valves and the fitting. So 7 plus 13, that is 20, divided by 100, that is 0.2. So in the same way you have to write all the lengths. So now we have to get the friction loss per 100 feet of trial pipe size. Friction loss per 100 feet of the trial pipe size. Since we know that our calculated GPM is 108, and based on our trial pipe size 2.5 inch, we have to write these values. So 108 GPM and 2.5 inch trial pipe size, we have to write the actual friction loss per 100 feet of the trial pipe size. So 108 GPM, 2.5 inch pipe size. So this is copper L, again same. We know that our calculated GPM is 108 and trial pipe size is 2.5 inch. So 108 must be somewhere here and somewhere here, and trial pipe size 2.5 inch, and go below you will find here. So the friction pressure drop per 100 feet is about 3.2, something like this. 3.2 something like this, you can calculate over here, that is 3.2. so we have to write this 3.2 friction loss per 100 feet on this trial pipe size 2.5 inch, based on this trial pipe size. So next we have 104.5 GPM and trial pipe size is 2.5 inch. 104 and trial pipe size is 2.5. It's same, almost same, just 0.1 before 3.2, that is 3.1. let's say 3.1 is the pressure drop, so 3.1 over here. And the next one we have C to D, we have 77 GPM and 2.5 inch trial pipe size. So we need to know what is the friction loss. So 77, 60, 70, 80, so it's over here 2.5 inch, almost here, it's touched 2.5 inch here. If we go below, it's somewhere before 2, maybe 1.85 or 1.9 we can take over here. So 1.9, so same over here, 1.9, 77 GPM, 1.9. So this is the actual friction loss per 100 feet based on our trial pipe size of 2.5 inches. So next column is the friction loss in equivalent length. Friction loss in equivalent length. So now we know that total equivalent length based on our straight length of the pipe and based on our valve and the fittings, and we know that the friction loss per 100 feet based on our trial pipe size. So friction loss in equivalent length will be, we need to multiply column 7 and 8, you will get the friction loss in equivalent length. So 0.69 into 3.2, that is 2.21, and then again we have 0.5. Sorry, this one is by mistake 0.85, it should be 0.085 because we need to add both length, that is 8 plus 0.5, that is 8.5. 8.5 divided by 100, 0.085, so it's by mistake 0.85, it should be 0.085. So equivalent friction loss in equivalent length, there will be 0.085 into 3.1, that is 0.26, and 1.62 into 1.9, 3.078, so 3.08. so this is how you have to write these friction losses in equivalent length for each section. So after that we have to add all these length. So since we know that the length to the most remote outlet is, what are coming in the most remote outlet? A to B, B to C, C to D, and D to E. This is not a part of most remote C to F. So A to B, B to C, C to D, and D to E. We have to add all these lengths. So A to B, that is 2.21, 2.21 plus, then B to C is 0.26, and then C to D is 0.38, and then C to F, no, we have to take D to E to the most remote outlet, that is 3.08. So 5.93. So as you can see that the friction loss in equivalent length is 5.93 over here for the cold water piping, and we know that the pressure available to overcome pipe friction representing by line J is 9.36. so we need to get the value, we need to subtract this pressure available to overcome pipe friction with this value in the column 9, that is friction loss in equivalent length, that is 9.36 minus 5.93 equal to 3.43. so this is the excess pressure available to overcome friction losses. So as you can see that this is the positive answer. Make sure that this value should always be positive. For proper designing of water supply, hot and cold water, this value should always be positive. So the excess pressure available to overcome pipe friction is 3.43 psi. So this value is positive. If this value is negative or not positive, then what you have to do, you need to change your trial pipe size and perform the calculations once again. So you need to balance this one. This should always be positive to make sure that your design is perfect. So the sizes which we have selected over here, 2.5 inches, all are good. So excess pressure available to overcome pipe friction is 3.43. So in the same way you have to do pipe sizing for hot water, and you have to check. You can see that 7.99 psi is equivalent loss, friction loss in equivalent length. So if you minus 9.36 pressure available to overcome pipe friction minus this loss, so excess pressure available to overcome pipe friction is 1.37. This is also positive, so that means our selected diameters for the pipes is correct, that is 2.5 inches, 2 inches, and 1.5 inches for hot water sizing. So this is how you have to do your water supply pipe sizing. This is as per International Plumbing Code IPC. So I hope you guys learned something from this video. For more videos, keep watching my channel and don't forget to subscribe. Thank you. Bye bye.